Yo, what's up, SUPA? Welcome to another day. Woo! All right. So today we're going to work on a little bit of math again. So we got to talk about some neutralization, some different types of titration, and then some little things about double replacement again. So this is just kind of a mishmash of a lot of different things. All right, and it's just using math. All right, so let's start with neutralization. So we've already defined this. This is a reaction between an acid and a base. And it will always produce a salt and water. It neutralizes the acid and base neutralize each other just to produce salt water. Now, in reality, this is just another type of double replacement. Now, there are a couple types of acids and bases I want to quick talk about. All right, so we have monoprotic acids and monohydroxy bases. Okay, so if you see this, okay, mono means one. All right, this means one proton. This means one OH minus. So monoprotic acids produce one proton. Monohydroxy bases produce one hydroxy ion. Now, example, hydrochloric acid. Okay, that's a monoprotic acid. It'll only produce one H plus because it only has one. NaOH. This is a monohydroxy base because it'll only produce one OH minus. Then we have diprotic acids and dihydroxy bases. Can you guess? It produces two protons and two OH minuses. Example, H2SO4. So our sulfuric acid is an example. So why does it produce? Well, it's got two hydrogens that it can donate. Example of a dihydroxy base, calcium hydroxide. Okay. And finally, we have triprotic, and they're really triprotic acids. There really aren't any trihydroxy bases, but there is a triprotic acid which produces three protons, which are three H pluses. And this would be H3PO4. So I just wanted to quick classify these acids and bases before we talk about neutralization, because they do play a role in our neutralization reactions. So I want to specifically look at the reaction itself, and I want to break it down. And let's just do simple. If I take HCl aqueous and react it with sodium hydroxide aqueous, it's double replacement. This H goes with the OH, and that's actually a liquid, and it produces NaCl aqueous. Right, so here's my water, and here's my salt. Now let's break that down. Okay, let's break this down. Right? This is an aqueous. So really this is H plus aqueous plus Cl minus aqueous, right? Because that's what it is in solution. This is also an aqueous. This breaks apart. So we have Na plus aqueous and OH minus aqueous. Now, this is a liquid, right? This is a molecular molecule, so it does not break apart. And then the NaCl is dissolved in that water. Now, if we look at this, where are my spectator ions? Where are the ions that are not taking place in the reaction? Well, I have Cl's on both sides. I have NAs on both sides. So those all cross out. So if I was to write my net ionic equation of this acid-base neutralization, it really would only be H plus aqueous plus OH minus aqueous is producing HOH liquid. Right, so this is my net ionic equation for neutralization. Now, if you have a di or triprotic acid or a dihydroxy base, it changes your coefficients a little, but it still has the same basic structure. You get this H plus OH producing just water. All right. So right along with neutralization, now we're really talking about titration. And titration isn't specifically used for acids and bases only. It can be used for other things. So let's talk about titration. So titration is used to determine the concentration of a particular solute in a solution. Now, in your regular chem class, you use this to figure out the unknown concentration of an acid or an unknown concentration of a base. Okay? It's not just that. We can do that for other substances too. So titrations can be conducted using neutralization, precipitation, or oxidation reduction reactions. Okay, so we can use any three of these types of reactions in a titration, right? Like I said before, probably this is the only one that you use in your regular chemistry class, okay, is neutralization, right? But we can use all of these. Now, we're not going to really be doing a lab with titration right now. We'll definitely do one when we do the acids and base unit. So titration involves reacting a solution where the solute concentration is not known with a reagent of a known concentration called the standard solution. Now, just to jog your memory, we usually do this in two burettes. Okay, so you have this, for those of you that don't remember, you have the long tubes, right? There was a valve right down here that turned it on and off. Okay, and we had two of them. Okay. And in our chem classes, we had just acid and base. And one of these, okay, so this was maybe an acid, this was a base. Okay, maybe this was our known. We knew the concentration of this one. This was our unknown, maybe. And I'm just making this up. So the acid, if we know everything about this acid, this is what the standard solution is, right? And we can use these burettes, okay, which is just measuring volume, to figure out the concentration of the base. Okay. So hopefully you remember using these burettes. We'll use them again this year. Let's talk about the equivalence point. So the equivalence point is the point at which enough standard solution is added to completely react with the unknown solute. So if this is my known and this is my unknown, I'm going to keep adding acid until all the base has been reacted. All right, and at that point, we've reached the equivalence point. Now, again, when we get to the acid and base unit, we'll talk a lot more about this equivalence point. All right, we need to talk about the end point. And the end point is just the end of the titration. All right, and the end point is usually very near the equivalence point, usually. And usually we use indicators. So probably, if we go back to our example up here, we probably used PHTH as our indicator, phenolphthalein. Remember, and this is clear in acid, and it's that pink in a base. Okay, so in this, usually when we use the acids and bases, we use phenolphthalein, okay, which is just an example and answer of a indicator. Right now, there are lots and lots and lots of types of indicators, and they can get very specific. Right, and we'll look at indicators a lot more closely when we get to acids and bases. All right, so the last thing I want to talk about is called volumetric analysis. So volumetric analysis is a method involving calculations based on titration. So now, when you were doing acids and bases last year, you used the formula. You used MAVA equals MDVV. The molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. Guess what? We are not going to use that formula this year. All right. So there are a lot of issues with this, especially when we get into weak acids, using weak acids and weak bases and stuff that's slightly soluble. So we're not going to use this. All right, we're going to use stoichiometry for all of these. So for our titration or volumetric analysis, we're going to use stoich. All right, so let's say, let's just look at this. We know if we have HCl and NaOH, it produces H2O and NaCl. All right, so we know that one of these plus one of these produces one of these and one of these. Okay, so what this is telling me is 1 mole of HCl is needed to neutralize 1 mole of NaOH. We have a 1-to-1 ratio. We can use this ratio to do our volumetric analysis. So let's see here. Let's try a problem. Calculate the volume in milliliters of 0.100 molar HCl needed to neutralize 50.0 milliliters of 0.250 molar NaOH. So remember when I told you, I've told this to you a couple times, you always want to get into moles. Okay, so if you're not sure where to start, get into moles. And we can get this into moles. We can say, hey, molarity equals moles over liters. So we got 0.250 molar equals X over, I got to convert that to liters, 0.0500 liters. And if we cross multiply, 0.0125 moles. Ooh, sorry. So we use 0.0125 moles of NaOH. Now remember, if we look at this stoichiometric ratio, for every 1 mole of this, we neutralize 1 mole of HCl. So that means I need, since this is a 1-to-1 ratio, that means I have 0.0125 moles of HCl. Now I can turn this back into liters. So now I know molarity equals moles over liters. This is for my HCl. I know what the molarity was. The molarity was 0.100. I now know how many moles of it I had in there, 0.0125 moles. I can calculate liters. Which is 125 milliliters. So this right here, okay, is called a volumetric analysis. Okay, so this is what we're going to be doing for our titrations and those different things. Okay, we always work in moles. So let's try another one that's a little more different, a little more difficult. Determine the volume of 0.250 molar barium hydroxide, aqueous, needed to neutralize 15.0 milliliters of 0.175 molar HCl aqueous. Now let's look at this equation first of all, because it's a little bit different. HCl plus BaOH2, it still goes to HOH and BaCl2. Right? But when I balance this, I need a 2 here, and I need a 2 here. So my ratio changes. So now for every 2 mole, I need 2 moles of HCl for every 1 mole of barium hydroxide. Right, so this time I have a 2-to-1 ratio, so that's going to make a difference in my answer. But I do basically the same thing. Right, so we're going to start by figuring out how many moles of HCl I have. So I use 0.00265 moles of HCl. Okay. So remember, I need twice as much. I need twice as much hydrochloric acid to reduce the barium hydroxide. So I have twice as many moles. Right. So because it's a 1-to-2 ratio of base to acid, I have to take this number and divide it by 2. Right? So I have to take that 0.00265 and divide it by 2. So that means I have 0.0013125 moles of barium hydroxide. Now that I know how much barium hydroxide I have, or the moles of barium hydroxide, now I can convert it back to liters. So I need 5.25 milliliters, okay, and they would be neutralized. Again, this is called volumetric analysis. All right, let's try another volumetric analysis that's not with acids and bases. So let's try this. The quantity of the chlorine anion, aqueous, in municipal water supply okay, so when I say municipal water supply, we're really talking about tap water, is determined by titrating the sample with silver ions. The precipitation reaction is Ag plus aqueous plus Cl minus aqueous goes to AgCl solid. I haven't even gotten to the question yet. Ready? How many grams of Cl minus aqueous are in a sample of the water if 20.2 milliliters of 0.100 molar Ag plus is needed to react with all the Cl minus in the sample. So again, this is really just stoichiometry. So, okay, we look up here, we have a 1-to-1 ratio again. So for every one of these, we need one of these. So if we can figure out how many moles of silver I need to react with that, I'll know how many moles of chlorine ions we have, right? And then we can get into grams, right? So the first thing we're gonna do is we're gonna figure out moles of silver. And it's just molarity equals moles over liters. We have 0.100 molar equals X over 0.020 liters, 202 liters, sorry. So that means we have 0.00202 moles of Ag plus. So now we know that it's a 1-to-1 ratio. So if I needed this many moles of silver, that means that that's how many moles of chlorine ions I have. So therefore, we have 0.00202 moles of chloride ions. And it wants to know how many grams we have. So now we're going to convert to grams. Moles equals given mass over gram formula mass. We have 0.00202 moles equals X over, Let's just use 35.5 grams per mole. It's only 3 sig figs. Cross multiply, and we end up with 0.0717 grams of chlorine ions in that sample. All right, so this is an important calculation, all right, that we do in testing water all the time. So when you test your water or you have it done, right, this is the kind of calculation they're going to do at the titration to see how much chlorine's in there. Right, but this is the math that they're doing. All right, I want to do a variation on the theme. So now, if you remember in my room, there are signs up all in my room saying, don't drink the water. Why can't we drink the water in my room? Well, it has lead. Right, and that lead, the amount of lead is too high in my water to drink. All right, and it will cause problems. Well, we can test, and I should make a lab for this. We can actually test how much is leads in a sample of water, right? Doing a volumetric analysis. And this is kind of a variation on that theme, right? So let's say we have a 1.0 liter sample of water is analyzed for lead. Right? So we go over to the sink, we get a liter sample of water. This is done by adding sodium sulfate in excess. So we just keep adding sodium sulfate. The mass of the PbSO4 precipitate is 300.0 milligrams. Calculate the mass of lead in the liter of water. And we could write out the equation, all right, but so let's go ahead and try this. So the first thing I'm going to do is I'm going to calculate the percent of mass in PbSO4. So the mass of the part, the mass of the lead is equal to the part over the whole times 100. Right, and I need GFM, so let's do that over here. PbSO4, I have lead, I have S, and I have oxygen. I have one of these and one of these and 4 of those, and we multiply. And let's just 207.2, 32.1, 16.0, add all that, multiply across, add all that up, and we end up with 303.3 grams per mole. So that's going to go on the bottom. And my part is my lead. So it turns out that 68.32% of the sample is lead. So I can say this now. Now that I know that 68.32% is lead, all right, I can say this. This is just making it easy. 68.32 grams of lead are in 100 grams of PbSO4. Right? Can I make that assumption? Sure, because it's 68.32%. I can also say this. 68.32 milligrams of lead are in 100.0 milligrams of PbSO4. So I know there are 68.32 milligrams for every 100 milligrams of PbSO4. Well, I don't have 100, I have 300 milligrams. All I need to do is take this number and multiply it by 3. And I ended up with 205.0 milligrams of lead. All right. Again, just lots of different ways to do volumetric analysis. Okay, so this is just another way using my percent mass. All right, so I want to deal with one last little thing. And these are called gas forming metathesis reactions. And these are not some you should know. Some of them I've already talked about. Carbonates and hydrogen carbonates with an acid. Okay, so these always are going to produce CO2, H2O, and a salt. Okay, so we already talked about that. We've actually done an example with carbonate, I think. All right, so let's say we have sodium hydrogen carbonate, and it reacts with, I don't know, how about HBr? Okay, so this is a hydrogen carbonate. It will always produce carbon dioxide, H2O, all right, and it's going to do the same thing. All right, we're going to take the Na from the hydrogen carbonate, and the Br so we would get NaBr as our salt. And then you'd go and have to balance it. All right, so these two, make sure that you know. So what if I have SrSO3 and I react it with an acid? Well, compare where in this case, this sulfur acts like carbon. So when you have an SO3, right, reacting with an acid, right, it's going to act like this guy did. Whoops. Yeah. So you're going to end up with SO2 gas plus H2O liquid. And again, we can get our salt. Okay, so careful with your SO3s. All right, because when you react them with an acid, they're going to act just like a carbonate, and they're going to produce these. I don't think you're going to see this. I don't think you'll see that, but it's possible that you'll see this sulfur dioxide. All right, but the SO3 is acting just like the CO3, so you can see how they're very similar. The third one you should be careful with that produces gases is when metal sulfides react with acids. Okay, so by a metal sulfide, we're talking about something like Na2S. I'm going to react it with an acid, about sulfuric acid. It's going to produce H2S gas. And it's just double replacement, right? But it produced this H2S gas and Na2SO4. So when you have this metal sulfide, that's what that is, it's going to produce a gas, H2S gas. And you should know that one. Now, there are three driving forces for metathesis reactions. Okay. And I haven't used this term before, but it's just another term for double replacement. Okay. That is just another term for double replacement. All right, so we said, when we first talked about double replacements, we know that the reaction is going to happen if a precipitate forms. Okay, we've already done that one. Well, we also know that this is going to happen if a gas forms. So if we do a double replacement reaction and it forms a precipitate, all right, that reaction happens. If we do a double replacement or a metathesis reaction and a gas forms, again, the reaction happens. The third one is the formation of a soluble, weak electrolyte or soluble non-electrolyte. And this is the one where neutralization falls. Because we're producing H2O. Okay. So that's why our neutralization, okay, happens, because we're producing this non-electrolyte of water. Now, another example of this one would be something like this. If I take HCl and react it with sodium acetate, NaC2H3O2, it will produce HC2H3O2, and NaCl. Okay, so this is a metathesis reaction. It's double replacement. It happens, okay, because this right here is a weak acid. Okay, so this would be aqueous. This would be aqueous. This would be aqueous. And technically, this is aqueous. But remember, weak acids do not dissociate completely. So we're actually producing HC2H3O2. Okay. Which means that double replacement reaction will happen. All right, so that's what we're going to stop for today. All right, and I hope you have a good afternoon.